Hi, I'm Charles Huang, and today is December 8th, 2012, and I'll be covering the MAST lesson template for Physics Standard 2G. Now, 2G is students know how to solve problems involving elastic and inelastic collisions in one dimension by using the principles of conservation of momentum and energy. And this is actually a standard that's very involved, so we have actually split this up into a couple different pieces, and we're actually approaching the tail end of this particular standard. Now, this standard, this learning target for the end is designated as students will be able to identify conservation of momentum problems and not only solve them but also be able to annotate and draw and lift pertinent data from the pros in order to set up these problems and solve them correctly. And these learning targets are also scaffolded for different designations as well. The medium students being presented with annotations and drawings already presented on that slip. And then as we approach ELL, SPED, and low students, these annotations, drawings are already provided, and in addition, they're also given completed examples or allowed to use completed examples in order to help them step through this exit slip. Now, this particular lesson, it will be fairly comprehensive and rigorous due to the fact that its main purpose is to complete a very long, involved, stepwise problem-solving structure that is an extension of the previous guess methods that they've used before in their other physics standards or physics problems, such as velocity and just the simple momentum problems. So this lesson is the 7th out of 9 in a 3-week series for the momentum unit. It ties back into energy by the whole idea, the pervasive idea of conservation of a number, of a quantity. And also, although the particular concept will not tie into any subsequent lectures because this is primarily an autonomous idea, the skills that they've been utilizing, such as solving for one variable algebraic problems, in addition to lifting out pertinent information from pros, will be definitely very helpful and be seen again in subsequent lectures. So those skills that they practice here will definitely carry on over to the next semester as well. Now, the structure of this lesson will follow the traditional CMAST lesson template with the hook, the IBE, IML, active practice, and closure with the DSN integrated throughout. Their DSN takes the form of their composition notebooks, where they're asked to, on the left side of each of their notebooks, every day, a new page, all of their Catalyst and Think pages, their own produced work that from their own thinking goes on the left side. Anything that I produce or I present in terms of work or model work will go on the right side. So notes, lectures, and all of the worked out problems that I present on the whiteboard will be going on here. So in the hook, we showed a video of Cannonball Frank Richards with
I'm the old roof saying, so long and you're burgling.
Now, this is to demonstrate the idea of this momentum, this motion being transferred upon a key event to another object, which takes that momentum and does what it will with it. Now, students went very crazy over this hook and set up the rest of the lesson very well. Now, the second half of the Catalyst involved 2 quantitative problems where they were actually asked to solve these momentum problems using P equals mv, which is a very strong or very important prerequisite in order to attack these conservation momentum problems. Now, this concept was presented in prior lessons, and we actually had an exit slip testing this the lesson before. And in that lesson, we had 17 out of 19 students correctly solve these problems to fidelities and demonstrate mastery, which is 89%, which is above the baseline 80% required for mastery in our classroom. Now, in order to facilitate a little extra practice, though, we presented that in the Catalyst as well. And in the Catalyst, the very Catalyst, we had 19 out of 20 students at the beginning of the lesson correctly solve the momentum problems. And the one student that actually did fail to do it correctly was an ELL student who misread the problem and misidentified a given. So after fixing that, we fixed that. We identified the root of the problem. Now, as cited in J.R. Baird's work in 1986, students become more informed, purposeful learners and exert greater control over their learning when actually focusing on a metacognitive skill, so their ability to think about their own thinking. And as such, after they completed the Catalyst, they were a couple students were cold called and asked to share their answers with the rest of the class. And upon every answer, I requested that they stretch their answers with incorporation of academic language, academic discourse, or some kind of synthesis of new information or a new idea that could be shared with the rest of the class. So asking them to stretch their ideas in order to help them step through their own thinking. Now, in the IBE, students were shown a Bill Nye episode. very similar concept to the video of the cannonball that we saw, where students saw transfer momentum from one object to another object. And accompanying this video was a worksheet where questions that are very important to identify when setting up conservation of momentum problems were asked. Now, this is the investigation before exploration piece, where students were not given any answers and were actually tasked to differentiate themselves into different member A, member B, and answer these questions as they were shown this video clip repeatedly. Now, directly following this, subsequently, we had a JTPS portion with a driving question: is momentum being transferred or moved in the situation, where students were asked to justify their conclusions. Now, according to research from Slavin in 1983, he indicated that among cooperative learning methods in which students study the same identical material together, the only methods that really provide consistent results over the control method was to provide rewards for group members' individual learning. So as such, I circulated through the class and kept a lookout for academic discourse and helpful languages. And then when I ever saw evidence of that, I provided a stamp and also gave them a class dojo point that they can use later to use in an auction for prizes later in the year. Now, as a DSN reminder after this, after we successfully completed the IBE portion, we retouched on a very important point or a maxim that they were introduced to a couple lessons ago, just to bring it back to the front of their minds, and especially at a time where this information is very relevant, they were asked to put it in their DSN compilations in their composition notebook. This idea was when there is no net force, linear momentum is conserved, which is the step 2 process of these conservation of momentum problems. Now, in order to get a quick check of this understanding of this familiar key concept without having spent too much time on it, students were asked to give me a thumbs up for a yes and thumbs up down for a no to answer questions about the presence of a net force in 3 successive pictures. One of a bungee jumper, which was a yes because he's accelerating downwards. Cars on a bridge, which is a no because there is no acceleration in the vertical axis for these cars on the bridge. Nothing floating, they're not crashing through the bridge. And a football quarterback being tackled, which was a yes because he's accelerating in the direction he's being tackled. Now, the results for this was 19 out of 20 got the first one, so we did a little bit of tweak there, and then the next subsequent 2, we got a full 20 out of 20 of the entire class answering the questions correctly, so we moved on. Now in the IML, students were instructed to reference their IML portion of their DSN set, their accompanied their composition notebooks. Now, while students have seen most of the first couple steps that are involved in the conservation of momentum problems, a lot of them really just know how to go through the recipe, the cookbook of setting up these problems. So in order to help facilitate more understanding of the motivation behind why we do each mathematical step, I had them, as you can see here, I gave them space to present their mathematical evidence, but also, more importantly, the other half, the half of the worksheet, have arrows pointing down to different stretch questions where they're asked to articulate the motivations and the decisions why they do each step in terms of the mathematical setup. So some questions that really make them explore the reasons why they do each mathematical step and trying to ingrain in them and instill in them the idea that all these mathematical steps have an actual basis, have an actual reasoning behind why we do each one. Now, after this first initial part of the IML, which they did pretty well because they've seen that before, they were asked to attack this literacy prompt, where they went through their textbooks and read some pages, and they were indicated to answer these questions as they lifted them from the text. Now, Torgerson has research that states that literacy is best produced, but the best results in literacy are produced, especially when students are reading data or reading information on prior knowledge that they already possessed. So based on that, we presented a little more literacy opportunities in there. And then following that, after they answered these questions, we put this on the side burner for a little bit and then had them attack actually we went to this bottom page right here, this one empty blank question prompt, and they were given actually this model card which had the last 2 steps. The step 5, solve for the unknown, and step 6, check for your answer, already worked out for them. These are the 2 steps that they are missing in their conservation of momentum strategy, and because these are operations that they're very familiar with, this solving for the single variable algebraic problem, they've seen that in the previous guess methods for other physics problems, and checking your answer. these were not terribly new. So instead of spending a lot of time in direct instruction, we utilized the model cards in order to help them get to the final answers, which they did pretty well. Now, after that, subsequently, they were asked to try 2 practice problems in addition to that. So after that exemplars were placed on the board, and they were asked to critique their own work and encouraged to cross out wrong answers rather than erase and rewrite them in order to demonstrate their progress towards mastery. Now, embedded in these, in this lesson, in these active practices, after the 2 were completed, we used a formative assessment where students were asked to identify this qualitative problem, and also demonstrate mastery of the quantitative problem that we've been going over in class, the practice that we did for a good 30 or 40 minutes in class. Now, in this, we actually had 15 out of 20 students answer both questions correctly. Now, that's 75%, which doesn't meet the 80% criteria in our classroom, so we actually went ahead and stepped through this problem step by step and in a form of reteaching, a decision that was guided by this data, this formative assessment. Now, afterwards, according to research from Otero and Campanario in 1990, they discussed that there was better literacy and reading comprehension retention and performance on reading comprehension assessments when readers were tasked to identify inconsistencies in the presented readings. So in order to combine that kind of data and in order to further promote literacy and integrate it in with their mathematical problems, now they were presented with slightly altered problems where they were given all these numbers, and then they plug it in and eventually subsequently get to a point, the check answer, the check portion of their work. If the numbers are matching, then they know that this is consistent with the idea of conservation of momentum. If not, such as this example, they're supposed to indicate there's inconsistency with this momentum. Now, when we did this one, we had an 18 out of 20 with 18 out of 20 students show proficiency and mastery over this particular piece. So we decided to go on and engage in the active practice and prepare for the exit slip. Now, during the active practice, students were the low-achieving students were presented with this model card. Each individual student was presented with their own copy of this, and in it you can see that these little thought bubbles that are absent from the normal version of it. There are no thought bubbles here. In the thought bubbles, there's little motivations and explanation as to why we do specific steps, because this is typically the point where a lot of the students, the lower achieving students, do seem to get confused. So in order to mitigate that problem, we have some thought bubbles here to help guide their process throughout the mathematical steps. Now, afterwards, after we did the active practice, I circled around in order to gauge some progress. Students were still underutilizing vocabulary such as conserved instead using words like phrases like stayed the same. And when I when I saw these, when I identified these problems, I prompted them to adjust their codings in order to reflect this academic language. Now, after this practice was completed, I gave them these exit slips, as you can see here, these exit slips. And their proven behavior was to solve 4 out of 5 at least correctly, and with at least 80% of the class being able to do so. Now, the high achieving and the medium achieving students, got copies of this differentiated with the annotations already given for them. And then for the lower students, they were allowed to utilize this model card as help, as an aid, as a visual organizer for their work on their exit slip. Now, after we did that, the subsequent day, when we went through the data analysis, 19 out of 20 students completely successfully this exit slip, so we decided to move on. But in deeper analysis, a lot of students seem to skip this step, or get it wrong, and somehow they got the answer right, but they were not very explicit on the step 2 or step 3. So in further review, which will happen in the next lesson and the subsequent lesson after that, we're going to heavily spiral back to and really emphasize the step 2, step 3, the application of conservation of momentum, because although they seem to understand how these letters translate into these subsequent letters and then plugging in, they still don't seem to completely be comfortable with the idea of what's going on in this part of the mathematical process. So in regards to that, until next time, thank you, and I hope you enjoyed.